Okay. Okay, hello? Okay, can everyone settle down? Everyone please either find a seat or, make sure you're not blocking the stairs. So in the stairs, it can be at most a single file. Okay, so these are strict fire marshal rules. So just make sure that if you're in the stairs, you cannot be more than one single file seated on one side. Okay, well, welcome to CS70. I'm Umesh Vazirani, and my office is 671 Soda Hall, and and my office hours are Monday 1:15 to 2, and Tuesday 6:30 to 7:15. Meaning, in particular, after this class, I have office hours for 45 minutes. Okay? Now, let me tell you first, I'll start by telling you a little bit about the course, and then we'll launch into the first lecture after that. So, first of all, to run this course, it takes a lot of work, and in fact, what it really takes is a absolutely wonderful set of TAs who you have up there. We will, by the time we are done, have a dozen TAs who've been extremely carefully selected. They are, I have to say, they are extremely knowledgeable, extremely helpful, and these are the people you'll learn the most from in the course. So you should get to know them well, and you should find the right TA for yourself. Okay, so let me just say what the components of the course are. Well, the components, of course, include the lecture, where you are. But then there are 2 weekly discussion sections. Okay, so twice a week, Monday and Wednesday. So your first discussion section will be tomorrow. Now, we've done something different this time. So instead of assigning you discussion sections at random through telebears, you're free to choose your sections. So you get to shop around in this first, within the first week of class. On the course webpage on inst, etc., inst.ecs, you'll find a link to, a page about the teaching assistants. So there's a little blurb about them, telling you about them, and a little bit about their teaching philosophy. So now the discussion section is okay. So in the lecture you learn the material, but in the discussion section and in talking to the TAs through discussion and office hours, homework parties, you'll actually learn the material. You'll learn to internalize the material. This is where the true learning will happen, and so it's very important that you try to find that teaching assistant who really appeals to your way of learning, right, and thinking. It'll help you a lot. So do try to spend this initial period trying to deal with that. I should say one more thing. In this first week, especially tomorrow, you might find the discussion sections very crowded for 2 reasons. One is, of course, people won't go perfectly 30 to each one. You might have some discussion sections overcrowded. But then we are also trying to process a number of students who are not yet in the class but who've petitioned to be in the class. We'll probably have that prepared by later tonight or tomorrow. So we are trying to pin down the last resources, teaching assistants that we need in order to support that extra group. And so we'll let you know how many, which and how many of you actually get to be in the class. Okay, so that's discussion for tomorrow. Now, there's homework parties, which is where you would that would be on Friday. There's one Friday afternoon. There may be another one on Friday morning. It would be in the Wozniak Lounge, and so currently there's one Friday 2 to 5 in the Woz, and that's where you'd be working on your weekly homework assignments together in groups. Okay. There's of course office hours. Where you get to meet your TAs face to face. And the last component of this course is the course notes, as opposed to a course textbook. Okay, so the course notes are fairly comprehensive. I'll have them posted well in advance, so they'll be posted usually weeks out in advance, but the course notes are being substantially revised this semester. So I'm going through them. I've already revised quite a few, but we are going to sit down and revise many more of them. And so the course notes you see well in advance may change by the time we get to that lecture. So, you should, you're free to read them in advance. They'll give you the right idea. But if you want to know exactly what was in the course notes, it might change, and sometimes it might change dramatically. Okay, so always look it over after the actual lecture. Okay, so these are the actual components of the course. Now, what are the actual tasks that you would do in the course? What is it that how do you actually learn the material? So as I said, the most important task here is the weekly homework. So this will typically be handed out Monday and due the following Monday at noon. Okay, so if you go to the course website, there's already the first homework assignment is posted, and it's due next Monday at noon. Now there's a second component to this, which is online. There's weekly assignments, and these are strictly optional. So they're strictly optional, but they can count for a certain percentage of your grade. So how does this work? Well, the online assignments are meant to help you get started. They give you, they are easier, they get you into the material, but they also are auto-graded. So as soon as you put in the answer, you get an immediate response, so you get to know whether you're on the right track. It's very helpful. But if you feel that you can skip it, you can skip directly onto the weekly homework, and your homework grade will be based only on your weekly homework. If you wish to do the online assignments and they are simpler, that's fine. Part of your grade would come from that. Okay, it's prorated either way. Now, there's a third part of this which of these tasks, which is, to my mind, just a part of it. It's almost as important, which is the grading of the weekly assignment. Or let me call it self-grading. Okay, so after the homework is due, you'll get back. At that time we'll release the solutions on Monday, and you'll have until Thursday to grade the homework you turned in. Okay, so based on the solutions, you'll assign yourself points. And what the readers will do is they'll spot check you and make sure that you're doing the reading, you're grading yourself well. Okay, the way it'll work out is that if you want to maximize your scores on the homework, your eventual scores after we are done reconciling everything, your optimal strategy is to give yourself the correct grade. If you give yourself too high a grade, your eventual grade will be lower than it should have been. If you give yourself too low a grade, it'll eventually be too lower than it should have been. Okay? Okay. Now, why do I think of this as part of the learning process? Well, it's part of the learning process because, one of the most important things here is, after you're done with it all, actually trying to see, even if you got the correct answer, reading what the correct solution was. Because sometimes the correct solution might be a lot simpler than you had it. Or it might make something click in your mind. It will clarify things for you. That's where the learning really deepens. And so this is an essential part of the process. Okay? Now, one other thing we have occasionally in this, as part of this weekly homework, is labs. Okay, what this would be is a short programming assignment that's meant to sort of get your hands wet and to give you a concrete feel for what we are working on. Okay, just so that it makes things sit a little more clearly in your mind. Okay, so just a little bit of bureaucracy here. So in terms of how much do each of these things count? Okay, so the homework will count for roughly 20 of your grade. Okay, and of this, you can have, if you wish to do online homework through the semester, then you'd get we'd give you 5 points for your online homeworks and 15 for the written. Or the way you can think of it is, at the end of the day, you will get the max of what you got out of 20 for your weekly assignment, or what you got out of 15 for your weekly assignment, plus 5 for your written. There's midterm 1, which is 20, midterm 2, which is 25, and the final, which is 30. Okay. Now, there are dates for the midterms which are on the web page. I think midterm 1 might be February 17th, and midterm 2 might be March 31st. Okay, so okay. Questions? Yes. Yeah, so somebody noticed. Okay, so yes, I'm missing 5% there. And the reason I'm missing 5% there is I'm not entirely sure. Okay, so it may get added to the final, but I'm hoping to find a much better use for that 5%. And so if you have ideas, let me know. Okay. Yeah. Okay. More questions? What am I doing here? Okay, so what's CS70? CS70 is discrete math and probability theory. So if you look up discrete in the dictionary, you'll see careful, subtle, unobtrusive. And then you'll also realize that you looked up the wrong word, because this is discrete. Okay. So, discrete means separate and distinct. Okay, so So you should think of discrete versus continuous. So for example, discrete would be something like the integers or the real numbers, or the natural numbers. So remember the natural numbers n, or the integers z, which is continuous would be something like the real numbers. Right? So it's just the continuity of the entire line. Or for example, discrete would be something like 0 and 1. Whereas continuous would be the segment between 0 and 1. All real numbers between 0 and 1. So you might denote it by, usually it's denoted like this. Okay? Now, so why are we studying discrete mathematics here? Well, here's a reason. It has to do with digital versus analog. Okay? So discrete math is the mathematics behind digital computers. Okay? It's not only the math behind digital computers, it's the math that actually historically led to digital computers. And it's the math that's used to do a lot of the things that we do today on a digital computer. Okay, so it's very intimately tied to computation and to digital computers. And that's why what we are doing in this class is we are trying to learn both discrete math, but also trying to meld it together with how it comes up in the context of computers. Right? Some of the discrete math was developed long before digital computers. But then today, a lot of discrete math is being developed as a result of digital computers. So it's a highly enmeshed process. And so somehow, you can study discrete math by itself, but it's much more powerful to study it in the context of digital computers, and that's what we are doing in this course. Okay? All right. Now, there's another thing that we're going to be doing in this course, which is we're going to be talking about proofs. Okay. Proofs are a way of telling whether something is true or false. Okay. And again, there are many ways of getting at the truth. So there's a scientific truth. That's one way of getting at the truth. Of course, there are other truths. Poetry tries to get at some kind of truth. Literature does. Religion does. But this is a very different kind of proof that we try to get to in mathematics. We try to get to, in some sense, the goal is to try to get to the absolute level of truth, a really absolute level of truth. How do you get to it? Okay, so that's the goal here. And in order to do that, one has to restrict the domain a lot. So because if you want to be that certain, you cannot be talking about everything. You have to talk about certain things. But then once you restrict to that domain, you can achieve a level of certainty which is remarkable. And sometimes making these restrictions gives you a lot of freedom to move. Now what you can do becomes, it's more channeled. That's what we'd be doing here. Now, it turns out this true or false that we are trying to tell between, this is sort of, again, there's an analogy to be made. Is it 1 or 0? It turns out, actually, that proofs in mathematics are very deeply connected to programs on computers. In fact, one could say that the very first programs were not written for a computer. They were written for a proof. It was while investigating the whole idea of a proof in the beginning of the 20th century. And these ideas about proofs, which led to this notion of, this abstract notion of a computer, that's what eventually precipitated the invention of the computer. Okay? So this is what I mean by this intimate tying between these two fields. And so this is one of the things we'll explore in this course. Okay, so where do these ideas fit into computation, into computers? Well, I hope what they'll do is they'll help you expand your ideas about what computer science is. I believe your courses so far have already done this in a really admirable manner. 61A does a wonderful job of, taking possibly, people might come in with ideas about computer science as being all about programming or building hardware, but there's a lot more to computer science. It has to do with artificial intelligence. It has to do with how do you design the algorithms that make computers be what they are. How do you deal with complexity, right? Which is really the one major problem in trying to make computers run well. How do you deal with this problem of big data, which is sort of the major, pervasive, most important question today, right? Issues of abstraction. So these are sort of the issues we'd be touching on even more in this course. Now, the ideas that we'll talk about, they have to do with I said already they have to do with the history of computer science, but it's much more than that. There are techniques that we'll talk about techniques that are used in across a branch of computer science, and these techniques are increasingly important to the future of computer science as it gets more and more connected to the rest of the world. So, okay, so these techniques would be used, for example, in analyzing algorithms, in designing codes. So how do you store information on an unreliable medium? How do you transmit information over an unreliable network? So this is one of the most important problems in signal processing. One that you will learn about in your EE courses. How do you do cryptography? Right, and security, which is probably security is again one of the really important problems going ahead. How do you design efficient networks? Okay, so these problems. It turns out the answer to these problems, if you really want to solve them well, the answer, it lies in the properties of numbers on primes. Of prime numbers. So what we are going to be studying in this first half of the course is not just proofs and but also these kinds of discrete structures. Okay, and we learn how to solve some of these questions. Okay, each of these questions is a subject of an entire course by itself. But here, in this course, what we'll try to do is tell you in sort of a nutshell, in a very nice setting, in a simple setting, as much of the story as we can. So we'd be missing a lot of the actual details if you want to make things very fast, or if you want to, but what we'll be giving you is a self-contained story about it, something that actually works. And now you have to work much harder to make it work well, and then you have to take a whole course. But this will give you a whole template within which to view that part of it. And it'll also, in the process, introduce you to the main techniques that are used in this process. Okay, so what I'm trying to say here is, in all these ways, here's how you can think of a computer. You can, it's not, in some of these contexts, it's really not inaccurate to think of a computer as math in action. Right? So it takes the math and it sort of actually, it makes it concrete for you in terms of, it's now no longer something sitting on a page, but it actually does something for you, right? And you get a translation of that math into an action, which behaves sort of, if you didn't know the math, it would look like a magic trick to you. And if you know the math, well, there it is. It's personified. It's concrete in front of you. Okay, so that's what we're trying to do in this course. Now, let me just say, there's one more aspect to this course which is very important, which is problem solving. Okay. Now, problem solving skills. So, discrete math has an incredible collection of beautiful, puzzles and problems and challenges, which are a great way to learn and hone your skills in problem solving. Now, the right way to approach this is as fun, if you can. Some of you will find it fun, and some of you, if you put yourself in the right mindset, can think of it as fun. And if you can, it'll become not only much more pleasant for you, but it'll actually be easier for you to learn. You'll learn it at a deeper level. So what do I mean by these puzzles? So let me give you an example of okay. So by the way, these are skills that will stand you in good stead through the rest of your of your studies, because problem solving is really an important skill that you need for your courses going forward. But it's also an extremely important skill later in life. And okay, if you want to, there's also another way to say it, which is sort of sounds a little more crass, but interview questions. They love to ask you problem-solving type questions. So let me give you an example from several years ago. This was a popular interview question during Google interviews once upon a time. I'm sure they have updated these long since, but this is a particularly nice one. So the problem is this. It's a simple problem. There's a bridge in the night. It's foggy. There are 4 people who want to cross it. One of them is sort of young and light and can cross it in 1 unit of time. But remember, the bridge is rickety and it's missing some planks, and it's over a gorge, and and these 4 people, I forgot to tell you, have only one flashlight between them. And moreover, the bridge can't support more than 2 of them at a time. Okay, so there are 4 people, at most 2 at a time, can cross, and 1 flashlight. Okay, and the second one takes twice as long to cross. The third one has a bum knee and can't do it faster than 5. And the fourth one is really scared of heights. So, that's going to take 10. Okay? The question is, can you get them across, all of them across in 17 units of time? So, you look at it, and what's the obvious thing to do? Well, you'd say, well, look, that's the fastest one. Obvious thing to do. 1 takes 2 across, comes back. Takes 5 across, comes back. Takes 10 across. How long does it take? 1 takes 2 across and comes back. So 2 plus 1 plus 5 plus 1. Oh, wait, how much did we do? Plus 10. Is that how much it takes? Wait, how much is that? Okay, that's 19. And surely we can't do better than using the fastest one. So there's no other way to solve the problem. Oh, sorry. Was it? Sorry, was it? Let me see if I got the numbers right. I seem to have copied them incorrectly. So, 1, 2, 5, 7. So let me use the ones that I have here because I'm not sure whether these work at all. So let's see what happens with this. It does. Okay. So should I leave it like this? Okay. Oh, yeah. Okay. Yes? So, yeah. It has a solution. Oh, tell me. 1, 2 go across. Okay. 5 and 10 go across. Oh, then 2 goes back. Okay. Okay, 2 goes back. Yeah. Okay. Ah, good. Oh my goodness. Wow, well done. So just to make sure everybody understands, 1 and 2 go across. How long does it take? It's the slowest guy, so it's 2. 2 goes back, takes him 2. 5 and 10 go across. That's 10. 1 goes back, 2. Right? So how much is that? Oh, 70. Okay. Okay, so okay, so let me say a little bit about how this course is organized. You know, what the policies are. You know, how the policies. Sorry, I don't want to speak about course policies. I want to say how the policies are organized. You can read about the course policies on the web page. Okay, but what is it that makes the course policies what they are? So, by the way, first of all, before I say anything about the course policies, you should really realize that this is a fairly fast-paced course. Okay, so it's fast, covers a lot of material. It's a lot of work. The history of this course is it started off as a small experiment. We wanted to create this course. We created a small honors section. Okay, so it was very, very fast-paced and very interesting. And then we didn't want to throw away all the interesting parts. So we tried to keep as many of the interesting parts as possible while getting to them in a systematic way, you know, so that people could get to them even if they hadn't seen a lot of material before. So that's what we're trying to do here. But what this means is that in order to keep up with this, you have to have the minimum background, which is sufficient mathematical maturity, you know, some programming experience, and you have to have enough time to actually work on the course. Okay? So the course will easily consume over 15 hours for many of you a week. You know, the homeworks for the average person will, just working on the homework alone may take something like 8 hours. Of course, there are the lucky ones of you who might just look at the homework and say, yes, I can solve it in an hour. But you should really be aware that in order to learn this material, it'll take you a certain amount of time. Now, the second thing I should say is that if you find yourself falling behind, it's not going to get easier. It's going to get tougher as you go along. So you should make realistic allowances for this going forward. So what are the realistic allowances you can do? Well, for some of you, not many of you, another possibility might be taking a course that just focuses on one part of it, which is discrete math. And there's a wonderful course in the math department that does this. It's called Math 55. So you would not see this kind of integration into EECS that you would see here, but it might be perfectly good for your purposes, and that's another way to go. And that might be a better choice for you because you'd learn the material at a deeper level, given wherever you're starting from. So that's one possibility. The second possibility is when you find yourself falling behind, you create more time. And there are many ways you can do this. But the most important thing is if you find yourself falling behind, create time as soon as possible, because the later you leave it, the harder it'll be for you. And, you know, it's not just the results. The total amount of work you'll end up doing will be much, much larger for much less reward. And so, you know, you can try creating time in various ways, but one of the good ways of doing this is looking at your schedule and seeing whether it's realistic. Are you taking too many courses? So one way of creating more time is drop a course, another course other than CS70. Third way of creating more time is drop CS70. Okay, but, and then try again. Okay, so why would that be a good idea? Because in the meantime, you can achieve the kind of mathematical maturity you need in order to succeed in the course. And this is a very important thing. It makes the difference between whether you're climbing uphill all the time and it's a chore and it's a pain, or whether it can really be fun and you actually learn the material. And it makes a huge difference. So this one decision is a very important decision for you, and you should make it carefully if it comes to that. Okay? So, all right, that's one aspect of the policies. Now, this course is very much about learning to do things. You're going to learn a whole set of skill set, a whole new skill set, ideally. And hopefully you'll really enjoy the course. You'll really enjoy these new skills. And these are going to be extremely important skills. Now, so this is the central goal of the course, is to make sure that you learn as well as possible. So this is why there are some very important aspects to this course, which is how the course is organized with respect to the homeworks, the homework parties, the discussion sections, the TA office hours. The TAs put in an incredible amount of work doing this for you, and you should be trying to make use of it. One of the things that this means is that, there is no embarrassment while learning. So it doesn't matter if you say, I don't know. That's completely fine. Okay? So there should be absolutely no embarrassment about it. There's no shame about it. And there's no shame in how long it takes you to really get to the concept. The question is, how well do you get to it at the end? Some of you might get it immediately, and some of you might take 2 hours to get it. But if it is the case that at the end of the 2 hours, this person got it just that much better, it became so simple and so supple in their minds, then they can move forward much faster after that, right? So remember, it's not how soon you got to this next step, but how soon you get to through the whole thing. That's what matters. There's another aspect to this which is very important. This is again this collaborative aspect to the course. This is a very important aspect to the course. In these weekly homework parties, you're going to be working together in groups on the homework, right? So you'll work together trying to solve problems together. And the reason is you learn from each other as you do this. You learn how to do this problem solving. It's a very important thing to do. Now, how should you choose these groups? Well, the typical way to do it is just to pick a group that you're most comfortable with, you know somebody, and then you stick to that. You might be that you might be cheating yourself out of an opportunity there, because one of the great benefits of this whole setup is that you can go into the homework party and you can join a new group each time. You can join different groups and you can experiment. Now, there was a very accomplished sports coach who once told me something very interesting. He told me, practice against somebody much better than, just a little bit better than you. It'll make it'll improve your game a lot. Then he said, also, practice with somebody who's not as good as you. It'll also improve your game. Okay, and this was an extremely wise thing to say, even in that context. And the reason is, when you're practicing with somebody who's better than you, it doesn't leave you time to settle. It gets you out of these patterns that you've fallen into. It sort of disrupts those patterns, and you're forced to do things differently just to keep up with them. That's a good thing. But then when you're playing with somebody who's not as good as you, then everything is more comfortable. You have so much time. And as they are doing their thing, you're playing and you change something, you do something differently, and suddenly you're much more comfortable doing what you were doing before. It becomes easier. So both these things are extremely useful to do. Now, in the context of doing CS70, it's even better than that, because when you're working with somebody who's not as who's not quite as good at you as problem solving, you'll find yourself explaining things to them. And when you explain things, it makes your ideas sharper and better. And you'll gain from that as well. So it's even more useful than in the context of sports. So see if you can make use of some of these, strategies for doing things. Okay. All right. So now, in terms of sections, let me try to say something that there's. As I said, all the TAs have their own styles of teaching. You should shop around. You'll see their own blurbs about what their teaching philosophy is. Use that as an initial way to match up with them, but then shop around. But then, in addition to that, what we wanted to do is possibly, if there's interest, have a couple of different kinds of sections. So maybe we could have one kind of section, maybe one or two of those sections, which are sort of gentler for people who maybe feel that they'd like to brush up on their background a little bit. Okay, so I'd like to see a show of hands of how many people would think they would genuinely be interested in such a section, in attending it as their, so what I mean is not as a supplement to their usual section, but as their section. So it would be something that starts off more gently, but it'll be covering the material of the section, maybe more gently and maybe not as fast. So how many people would be interested in that? Sorry. Okay, so what we'll do is start off with one such section this week, and then we'll see how much more demand. It seems like there's demand for one or slightly more than one section, but if there's more demand than that, we'll increase it, and otherwise we'll keep it at that. Now there's a second end of the spectrum. How many of you would be interested in a more advanced section where? Here's what I mean by an advanced section. It's still your regular section. You go there to cover the stuff that you would normally be thinking about, except that maybe you feel pretty comfortable with this material, and instead of having an hour-long section, it's enough for you if the section was 30 minutes or 40 minutes. And then the rest of the time is spent on something fun and something which says, well, look, we got you to this point, but if you look just a little beyond this, look, here's this very interesting thing. It's cool, and it applies in this way to the things that you're doing. So how many would, again, not just to shop around, but how many of you feel that you can see yourself in steady state in such a section? Okay, so again, enough for about one. And now let me change the question for an advanced section to a different one. How many of you feel, look, you don't need a regular section. If there was an advanced section which said, look, here's the stuff we have taught you, but around this stuff, there's all this cool stuff. And, each time we are going to talk about that, fun, interesting stuff, but it's related to what we talk about in class, but it's not what we talk about in class. How many people would like that? Okay, good. So, all right. So any questions at this point? Yes.
For the interesting section, would that information be outside the scope of the class?
No, I'm thinking it would be within the scope of the class. So it would be the first kind of section where it's what you need for doing this course, except with a little bit of supplemental information or supplemental ways of thinking about things. And I should say, by the way, often when you look a little further, the stuff that you're doing can become much easier. So there are some cases where you go a little bit beyond, and the things that you're doing now in this class suddenly appear easier. But but to go a little beyond, you have to know a little bit more. So some of you might actually find that doing the advanced section actually makes things easier for you in class. So it's one of these sink or swim things. If you can swim, it might become much easier for you. But if you can't, well, just don't do it. Okay? Okay, so one last thing before I start on the rest of the class. So, of course, there's so I talked a lot about collaboration. There's a limit to collaboration. So you're allowed to discuss everything. The limit to collaboration is you can't share your work with anybody. So what does this mean? Anything you write is not shared, right? While writing it, you're not sharing, right? So meaning you can collaborate all you want while you're solving the problems. When you write up your answers, you write it up alone. Okay? So this is a very important line. It's taken very seriously. Crossing it has tremendous consequences. So you should know that crossing that line is considered cheating, which is not a good thing for many reasons. It's also not a good strategy, Okay, so it's not a good strategy in the context of this course because eventually most of your grade depends upon work you'll do by yourself in the exam. So knowing what you can do by yourself is extremely important. You've got to do that. But also, I think most of you will find that when you go out into the real world, the parts of the real world where you're going to be will greatly reward collaboration, but not cheating. So, it's just a good strategy. It's a good policy, and it'll probably feel good as well. Okay, so back to let's start on today's topic, which is propositional logic. Okay. So a proposition is a statement that is either true or false. Okay. I'm sure everybody here knows statements which can be both true and false. You come across them all the time, and well, it would be hard to come across statements which aren't ambiguous in literature, in poetry. What would Shakespeare be like if he was forced to write everything which was either true or false? In songs, in philosophy, even in some of the sciences, biology, right? So, you look at people will tell you, biologists will tell you, look, we don't, there are exceptions to everything we say. We don't really talk about absolute truth, right? So where do you go to find absolute truth? Well, this is where you go to find absolute truth, because you define it that way. And these are the only things we'll talk about. Okay? So, propositions, 1 + 1 = 2. Angles of a triangle sum to 180 degrees. For if n is a non-negative integer, then n squared plus n plus 41 is prime. For any integer n greater than 2, n can be written as a sum of two primes. Washington, D.C. is the capital of the US. Berkeley is an interesting city. Okay. So let's see which of these are propositions and which of them are not. Number one. Yeah, of course. Number two. Yeah. Well, I'll say yeah for now, but you can, people quibbled over it over the ages because it actually depends upon in which geometry. Is it a Euclidean geometry? Is it a non-Euclidean geometry? So this became a conundrum. But then, that was just, we haven't specified it well enough. But once you do, then it's a proposition. Okay, so it's close enough. If n is a non-negative integer, then n squared plus n plus 41 is a prime. Yes, it is a proposition. By the way, is it true or false? It's false. Yeah, so it turns out this is a very interesting case because, if you actually substitute n, so you do n equal to 0, 1, 2, 3, 4, 5, 6, etc. What are the values? It's 41, 43, 47, 53, 61, 71, 83. Turns out these are all primes. You keep going, you can keep going and you sort of end up getting primes. When do you stop? When would you stop if you were a biologist? When would you stop if you were a physicist? Right? And when would you stop if you were a mathematician? And then there's a question, when do you stop if you're a computer scientist? Right? Is a computer scientist more like a biologist or more like, which one makes sense? Well, it depends upon which context. That's what we're trying to get at. Okay, so the answer is eventually, when n becomes large enough, you get to non-primes, but you have to go pretty far. It's really remarkable. Okay, what about this one? Is it a proposition? Number 4. For any integer n greater than 2, n can be written as a sum of two primes. It's either true or false. Either it can be or it cannot be, right? Either every integer can be or it can't be. Is it true or false? False. Anybody think it's true? Anybody else think it's true? Somebody there? Huh? This, number 4, is called Goldbach's conjecture. It was made by Goldbach in 1742. Conjecture, he said, I think this is true. People have been working on it since 1742. Nobody knows the answer. Nobody knows whether it's true or false. Okay? So the fact that it's a proposition doesn't rely on the fact that we know whether it's true or whether it's false. It can be the case that we don't know whether it's true or false, but it's still a proposition because we know whatever it is, if it's not true, then it's definitely false. If it's not false, it's definitely true. We just don't know which one. It's okay. It's still a proposition. Yeah? Washington, D.C. is the capital of the U.S. Proposition? Yeah, all right. Okay. Berkeley is an interesting city. Most definitely yes, isn't it? Isn't it an interesting city? No? Okay, well, okay. I would have thought there was more unanimity about it. But the point here is, even if everybody considered Berkeley an interesting city, this would not be a proposition. Because there might be somebody who doesn't. It depends upon what interesting is. Yeah, right? What's interesting to one is not interesting to the other. In fact, that's what you just told me. So it's not a proposition. Right? So I hope that makes it clear what's a proposition. What do we mean by proposition? Now, by the way, often what we'll do is when we write such a proposition, we'll call it by a name. So we'll say, this is the proposition P. P is a proposition. It says the angles of a triangle sum to 180 degrees. Okay? So now we could say P is true or P is false. Right? Instead of having to say, this thing, this such and such is true, instead of spelling it all out, we just denote it by P and say, well, P is a proposition, it says this, and it's either true or false. Right? This is another proposition, we'll call it Q. Q is this proposition, it's true or false. Okay. Connectives. So given two propositions, we can connect them together, okay, using certain kinds of connectives. And the simplest ones are these. They are and, which is denoted by that, or, which is usually denoted like that, and not, which is usually denoted like that. Okay? So P and Q is true in only one case, if and only if both P is true and Q is true. Yeah? P or Q is false only in one case. P is false and Q is false. Right? In all the other three cases, it's true. Not P is true if and only if P is false. It's just like that. No, it's just okay. No? Okay, so now one thing that of course, these formulas you can connect more than two propositions now that you have two. So, for example, you could write P and Q, or not R or Q. Right? So you could chain these together in some way. So, for example, we had P and Q up there. P was angles of a triangle sum to 180. 1 plus 1 equal to 2. P or Q is 1. Is P or Q true? Well, both P and Q are true, so P or Q is definitely true. Okay? Yeah. Oh, this one, second one. Yes. So, very good. Okay. So what should the second line say? Second line is saying P or Q is, well, okay. So I could have said it slightly differently, which is what's being asked, and I'll say it differently. P or Q is true if and only if P is true and or Q is true. Okay? So actually, let me illustrate this to you with something, with a way we have of visualizing these connectives using something called a truth table. Okay? So we visualize it in a diagram by writing down P, Q, P or Q, let's say. Okay? So now, what are the possible values for P? Well, they are true, false, okay? So we just write out all the 4 values. And now for each one, we just say, so there are basically 4 cases. Either both P and Q are true, P is false, Q is true, P is true, Q is false, or both are false. And in each case, we just write down what's P or Q. Okay, so what is it? P or Q in this case is true. How about here? True, because all you want is there's at least one true, right? Either this one or this one. So that's true. How about this? It's true. How about this? It's false. So now, when is it false? Well, the only time it's false is when both of them are false, and that's what I wrote down before. Okay, so I was telling you this one, and then the question was, shouldn't you say it the other way? Shouldn't you say, for these, it's true when either one of them is true? Yeah? So those are the 2 ways of looking at it. Okay. Okay. Now, by the way, there's a rule of inference that you can do. You know, there's called modus ponens. Where what you can say is, oh, sorry, let me get there a little later. Okay, sorry. Let me introduce one more connective before we get there, which is implication. Now, this is probably the most interesting connective we have, and it's of the form P implies Q. Okay? One way of saying it is, if P is true, then Q is true. That's what it's saying. This connective is saying, whenever P is true, Q is also true. Okay? So now, let's fill in the truth table for P implies Q and see what is it actually telling us. So here's P, Q, P implies Q. Okay, false, false, true. True. False, true, false, true. Which order do I really want to do it? Let me fill it bottom up or in some other order because it'll be easier for you. Okay. If P is true, true is true. Is P implies true telling us something correct? Yeah, because P implies true was telling us whenever P is true, Q has got to be true. It's saying something correct, so it's true. How about P is true, Q is false? It's false, right? Because P implies Q is telling us this is true. Whenever this is true, you have every right to expect this to be true. In fact, you can demand that this is true. And when it's not true, you can go back to P implies Q and say, that wasn't right. You know, what you told me was not right. So P implies Q, you're false. Right? So that's the way to think about it. Now, what about false, true? Doesn't matter, right? Because here, P implies Q is not telling us anything. It's not. All it's saying is, look, whenever P is true, I'm going to guarantee that Q is true. But here P is false, so P implies Q has no obligations to you. Right? What it told you was the truth as it knew it. So it's true. How about false, false? Same thing. P implies Q has no responsibility when P is false. So it's vacuous. So this is called being vacuously true. It's true just because it didn't even say anything. So, why should we hold it to account? Okay. Now, let's look at one other thing. Oh, sorry. Okay. Not Q implies not P. Okay, so this was P implies Q. That was not Q implies not P. Okay. So does not Q imply not P here? True implies true. Yes? Not Q implies not P. Oh, sorry. Not Q implies not P. So remember, we are going, sorry, I misdirected you. We are going from here to here. Right? So we were clever. We switched directions as well. We switched it to negation and we switched directions. So now, not Q implies not P. So this is true, this is false, implies true. Now, not Q not implies not Q has absolutely no responsibility. False can imply anything. So that's true. Not Q implies not P. True implies false. Now that's no good. So that's false. Not Q implies not P. False implies false. No responsibilities. That's true. Okay. So you look at these two columns of the table. And you see they're identical. Right? So P implies Q is the same as not Q implies not P. Okay? This is called the contrapositive. Okay? And this maneuver of going from an implication to its contrapositive is one of the most important things in proofs. Often, when you're trying to prove that P implies Q, and it's difficult to do, it'll turn out that this is easy to do. Okay, you'll come across many situations where, even though they are completely equivalent, it's just whether you're looking at something like this or like that, and you change your angle, suddenly it becomes much easier. Okay? Now, let's do one last thing, which is quantifiers. So, in many of the things that we saw so far, it was just a simple proposition. Except that, so far we've been talking about simple propositions. Except up there, when I wrote down these propositions, some of them were more complex. They talked about if n is any non-negative integer. Right? So how do you really express that in notation? Well, to do that, you sort of say, you use quantifiers. You say, for all n belonging to the set, what's the set there? Non-negative integers. z plus, right? It's saying n is any variable, any element of this, and then it must satisfy this condition. Okay, so what's the condition? N squared plus n plus 1 is prime. Okay, so this is a quantified statement. Okay. This is called a universal quantifier. It quantifies over the entire universe, and it says the entire universe, which is this is the universe of discourse. That's what we are talking about. It's the positive integers. Inside these positive integers, if that's our universe, everything satisfies this condition. Right? There's another quantifier called the existential quantifier. There exists x belonging to the natural numbers, such that x is greater than 5x. Okay? So again, we have a universe of discourse. That's the natural numbers. That's what we are restricting to. But now the existential quantifier just says, it doesn't say the entire universe that we are restricting to satisfies this property. It just says, inside here, I can guarantee you there's at least one element that satisfies this property. Okay? There exists x, which satisfies this property. Okay. Now, let me spend the last couple of minutes talking about something rather interesting that happens, which is, suppose you say there exists x belonging to n such that x is greater than 5x. Okay? There is such an element. So you have your universe, you are claiming there's such an x. Now, what happens if this is false? What would that be asserting? That there's no such element, meaning every x that you look at has a property that x is not greater than 5x. Okay, so let's call this statement P of x. P of x is the proposition that x is greater than 5x. So now here's a existentially quantified proposition which says P of x holds for at least one value of x in the natural numbers. That's what this is saying, right? So now what we're doing is we're saying, so this is a statement, there exists x, P of x. Okay, I'm shortening it. X belongs to the natural numbers such that P of x. Now what I want to do is take this proposition. This is a proposition itself. It's either true or false. And I want to say, what if I negate it? Okay, so what if I want to turn it around? So what if I want to say, not there exists x, P of x. Okay? I'm trying to say, it's not the case that there's some x such that P of x holds, that x is greater than 5x. Well, in order for it not to be the case, it must be the case that for every x, P of x doesn't hold. So this is the same as saying, for all x, not P of x. You see? So you can take this negation and you can move it through the there exists. And when you move it through the there exists, it flips from exist to for all. Okay? Yeah.
So the three bars means that they're
They're equivalent. These are the same statement. They have the same, they'll always be the same.
You can't use the same way as a regular system.
I'm sorry?
You can't use that symbol the same way as a regular system.
Oh, I see. Sorry, I'm actually improvising on notation here. If you want to be really strict about it, you'd write if and only if. Okay? So, actually, if you... but, loosely, this is what we often write, but maybe this is even more strictly correct. Yeah? Okay, so now, let me just state for you the general principle. If you think this through, suppose you had there exists x for all y, P of xy. This was your proposition, and you negated it. what you could do is you could just move the negation in one by one. And you'd say, this is the same as, you move the negation in, you get for all x, and then you would negate this piece, right? So you get negation of for all y, p of xy, right? But now, what's to prevent you from moving this negation in further? Same thing, same principle. You know, when you move it in, this quantifier flips. So you get for all x, there exists y, not p of xy. So this is a process by which you can just take your negation and move it past quantifiers, and the quantifiers keep flipping, and the negation keeps going further and further into the formula. Okay? Okay.